as I say, a little jingoistic, but it's got the closed captions on it, so we can see it. So this is one of, I don't know if it's the first jetliner post Second World War, probably early 50s, I would guess. De Havilland Comet. See the design, very unusual compared to jet planes these days with the engines, two engines inside each wing on each side. And was part of the growth of air flight following the Second World War, following 1945, initially with turboprop planes and then with jet aircraft. Jets were just coming into reality in 1944 and 45. And so these were planes that were flying, and all of a sudden, in the days of no GPS and spotty communications around the globe, if you can ever imagine that, some of them just didn't turn up at their destinations. And it was a big mystery as to why that was. Tragic mystery, of course. So how many of you believe that you used to be able to smoke on airplanes? In your lifetime? No, never, yeah. Certainly in 1980, you'd have to sit, well, I didn't smoke, but they'd sit at the back of the plane, so you could be sitting right in front. And of course, the seats had these little ashtrays in them as well, in the armrests. Anyway, so yeah, big changes. So I guess it's quite safe to smoke. I guess there are things that are a bit combustible in the plane, like the upholstery, but typically you don't have jet fuel fumes going on. So anyway, so some of these planes didn't arrive at their destinations, and I guess you can see where it's been looked at here. I guess this is the most interesting part of it, here. And so it was wondered why exactly that was. And of course, if a plane doesn't arrive at its destination and is in the ocean as a debris field, you don't get much information as to what might have happened, or you can try and do it. And so that was exactly the question here. And so what they did with a actual aircraft, I think, they recovered the pieces. Doesn't tell you anything about what's going on. I think it was in the Mediterranean off Italy, blah de blah. But then, tragic, of course. But then, yeah, okay, so this is it here. So then what you could do is you could fatigue test the plane on the ground. So this is a plane in a dumpster, cargo container, filled with water around the plane, and then the inside of the plane pressurized, so it's overpressured. We know that planes are pressured to be at atmospheric pressure, 100 kPa absolute. And as you go up in the atmosphere, the pressure drops, so there's a pressure differential that makes it want to explode. The Titan's submersible is the opposite, wanted to implode, going down to see the Titanic. And as a result of this post-test, with lots of cycles of pressurization and depressurization, you see what's going on. It was rumored to be the fact that the windows were actually square. Square windows have a stress concentration in the corner, and fatigue cracks grow from those, and the window pops and you get a massive depressurization. And as a result of that, that was the rumor of why these occurred. We learned from these, of course. Let's do this as well. Sorry, it's a bit of a gory day today, but these make lots of points. Aloha Airlines flight, whatever, a 737, those long cigar-like engines mean it's quite an old plane. But the deal with this was that it would fly between the islands, Hawaiian Islands. So lots of takeoffs and landings, so lots of pressurization, depressurization cycles as it comes up and goes down. And we know that when you do that, you fatigue crack things. Small cracks grow. Aluminum, the skins of these things are very strong, but when you get small cracks developed, those cracks get longer. And this, unfortunately, had a kind of a happy ending. It landed. I think lost one flight attendant, unfortunately sucked out, but barely made it, right? So certainly if you take the body off a car and just run on the chassis, so the body is an integral part of the structural rigidity of the system. So you do that for a plane, you have the same thing. And apparently, as it was going down, getting down quickly to land, it was slowly drooping a little bit. And that's exactly what this guy is saying now. So kind of a happy story. But again, I imagine pressurization, depressurization cycles also not helped perhaps by the fact it was salty air, although I don't think aluminum, like steel, is so problematic in the presence of seawater. So I think they got everyone down. So that's that. What else? Why planes crash? I guess that's what that is. Oh, we don't want that. Actually, let's do this. We talked last time, and I won't talk again, about something perhaps more terrestrial. The Malpasset Dam in the south of France that failed in the late 1950s, 59, and killed 300 people downstream. You looked at the dam break last time. There was another, I mentioned another dam that failed, the Resultant Dam in the Italian Alps. You can see where it is here on this map. It's right up here in the Italian Alps. Turin is somewhere here for the Olympics. I guess the next Olympics are Milan, and they'll be using the Italian Alps as well in 2 years' time. And so this failure was not due to the dam failing, but there was a big landslide that sat above it, was creeping, and then all of a sudden gave way. All of a sudden the landslide volume completely fills the reservoir of the dam, and as a result expels the water out over the top. And you can see the result if you read it. 1,900 or 2,500 people died. A mega tsunami, I'm not sure whether that's the right term for it, but they use it here. A wave of 250 meters tall was pushed out. So again, our public responsibility to due diligence in the calculations that we make. And finally, I guess related to this, lots of death and destruction today. So at the close of the Second World War, again, blah, 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 production of armaments in Nazi Germany, run by energy. Energy is the cornerstone of everything we do. And so energy in that particular context came from hydroelectric power. And the idea was that if you want to cut production of armaments, you go after the energy sources, just like in Ukraine right now, right? And the energy source was hydroelectric dams, so you have to break the dams. And they're not very easy to break. And what you need to do is you need to get an explosive at the base of the dam in the water, so the water, when the explosive goes off, has enough inertia that the energy from the explosive goes through the dam. If it sits on the top, nothing will happen. And so that's not an easy thing to do unless you can get it down just like skipping a stone on a lake. And that's what was done here. You see the end results for this. I guess I could have put closed captions on. But you have the bomb sit at the base of the dam. You have to get it by skipping it along the length of the river. I guess a reenactment of that. This is not real, right? It's video. But just like skipping a stone, have to get it right. Quite clever, really, to be able to do that. Fly low, drop it out, put some pre-spin on it, I believe, to make it bounce. And then I think maybe out of 4 targets, three dams were destroyed. And so also, I guess 9/11 is not quite in your, too much death and destruction today. 9/11 is not quite in your remit, right? That's 23 years ago now. I remember Hoover Dam on the border between Arizona and Nevada. Big, I don't know, not 300 meters, but it's a high arch dam. You used to be able to drive across it. And so immediately after 9/11, now there's a bridge that you take to go across from one side or the other, but not driving on the top of on the crest of the dam for clear reasons. So that's kind of what we'll talk about today, to try and get our heads a little bit around the idea of pressures on structures. So that's kind of if I open this. Okay. So we'll follow on from next time. Of course, you've been getting love notes from me, right? There's emails on Friday and Saturday. If we have questions, do we have any quick questions over that? We talked about it on Friday, right? But the midterm. pretty self-explanatory, yeah. Yeah, it'll be given to you. It'll be the same equation sheet that's in the review video. Yeah, I'll try and get the guys to post it on here as well. So the exact same equation sheet. So you know what you're getting. Okay. Sorry to spoil everyone's morning with that. Hey, but otherwise I'm a prince, right? All right. So today, let's carry on from where we were last time. Negative, positive, up or down in the fluid. We used those last time. So these depend on this depends on dp, dz. I like differential equations too much for my own good, right? This is the reason why this is that. It reverts to pressure being equal to P0 plus H unit weight. Unit weight is density and gravity. And so this is why these are so. We explained it last time. If we go horizontally, the pressures don't change if it's connected path. If it's evacuated, as in the barometer, the pressure is the vapor pressure. That's as low as it can get. And if we go up or down in the gas, typically because it's 1,000th of the density of the liquid, then typically we can ignore it. So you'll have some fun, I guess, in the homework this week doing that. So first week, fluid properties, including density, the one that was important for last week. Last week, fluid pressures at a point that rely on the fluids above you, not below you, but above you, the water above you, and also the gas above you, if you want to do it in absolute, or if you take it at zero pressure at the water surface, just the water above you. And so now what we might like to look at is understanding why, how we can use those to calculate forces on structures. And so this would be kind of what we're thinking about. We know that behind this little dam, there's a triangular distribution of pressures. We'd like to be able to resolve for the stability of it in some way. And so we'd like to be able to calculate what the horizontal force is. And so all of this week we'll devote to talking about forces on structures. So let's try and start with something that maybe makes sense from what we've done already. Let's talk about the de Havilland comet. See if it'll do it. Oh, it does, yeah. So pressure in the cabin, pressure in the atmosphere. Why don't we see if we can figure out exactly how we would analyze this? What we could do is we could draw a free body. Well, let me truncate the side of it. Let me just draw the free body to here. And with that free body, we could draw a bigger pressure in the cabin, bless you. This is the pressure in the cabin, and this is the smaller pressure acting on this imaginary line that we have here. And so this imaginary line merely means that this is the same force that's acting down on this shell. We've just isolated it. It's just easier to deal with. We could imagine that the diameter of the plane might be d of the cabin. And we can also maybe imagine that, running out of colors here, maybe that we're pulling down on the fuselage, which is we'll call this T. So we have fuselage pressurized inside. We isolate a free body, which is this diagram here. The pressure in the cabin is acting upwards on this structure. The pressure outside is acting downwards. Let me be consistent with my colors. And we have the strength of the aluminum pulling down at some strength. So we could write a free body for that just by writing the sum of the forces in the z direction are equal to 0. So it would be PA times D times the length of the fuselage, I guess. Actually, I'm going to write it slightly differently. Minus, we can resolve either up or down, minus PC times D times L. Plus T times 2, 2T. 0. So that's fine that we can write that as P. I'm going to move this to the other side. Let's do that. So 2T is equal to PC minus PA. This would be times L as well, right? Length. Times LD. And T is a force. It would be equal to a stress times an area, which is a thickness, times L. I guess not L, because L's already in that, right? And so if we substitute for this, it would be L times 2 times stress times T equals PC minus PA, L times D. And so how thick is the skin of a plane? Cabin pressure minus atmospheric pressure. I'm guessing a bunch of these cancel out. T over L times 2 sigma. I happen to know that the strength of aluminum is 200 MPa. We know, I think cabin pressure I wrote down as 20 or so, atmospheric pressure, that height is 20 times 10 to the 3 pascals. Capillary pressure is 100 times 10 to the 3. Bless you.
Thank you.
Length we don't care about. Taking a section. And 10, I can imagine 10 meters. I think I chose. So let's see if I get my math right. My math is horrible. So this is going to be 80 times 10 to the 3 pascals times 10 meters times 2 times 200 times 10 to the 6 pascals. 2 times 400. This is 80 times 10 to the 3. So this is 800 times 10 to the 2 over 400 times 10 to the 6 times 10, I think, right? 800 over 400 is 2. This is 10 to the minus 4. 10 times 4. What am I missing?
Sorry, I didn't see that you wrote 800 instead.
Yeah, just change this from this. 800 times 10, 2 times 200 times 10 to the 6, is that right? That's not right, is it? This is 200 times 10 to the minus. Let's get rid of that. Yeah, okay, it was good to show your vulnerability. So this is 800 times 10 to the 2. What am I doing wrong? equals 2 times 10 to the minus 4 times 10, okay, meters, which is exactly right. 2 millimeters. That's what it should be. It's written down here so small I can't see it, but that's what it should be. I think that's right. 2 times 10 to the minus 4 times 10 is 2 times 10 to the minus 3. 10 to the minus 3 meters is 2 millimeters. So, roughly. So that's all. So that's the kind of calculations we'd like to be able to do. It's no different than what I think you've done in your assignments with the bubble, where you had surface tension on the inside and the outside. I remember there was a question like that from the dim and distant past. Yeah.
Shouldn't that be 800 times 10 to the third?
It's 80 times 10 to the 3.
Yeah, and then you'd multiply it by 10, so would that be 800 times 10 to the 10? Or
80 times 10 to the 3 is 800 times 10 to the 2. And then 800 divided by 400 is 2. 10 to the 2 times 10 to the minus 6 is 10 to the minus 4.
don't we multiply it by the 10 meters of the distance? So
10 to the minus 4 times 10 meters is 10 to the minus 3. So the final result is 2 times 10 to the 3 minus 3 meters. These two are the same. Okay? Keep me on my toes, it's good. I need to be kept on my toes. Right? That's it. Yeah.
I know L ended up canceling out, but would that be defined as the length of the airplane?
Yeah, because the section repeats all the way along. Yeah, L is the length of the plane. Length of the cabin. Okay. And the cabins are cylinders, right? You look at any plane, it's a cylinder, then it tapers at both ends, because a cylinder is easy to produce. Yeah, okay. I think other things very quickly. We've also done. Whoa, didn't do that. So we talked about a balloon. If you think of a balloon in the same way, balloons are. We've talked about the ideal gas law. Pressure is equal to density times RT. A balloon rises because the density in the balloon is less than the density in the atmosphere. So the density of the balloon is equal to pressure divided by RT. And so the reasons that balloons climb is because you can make this density lower than the other one. So if you want this density to be lower than that, you can either reduce this pressure, which you can't do, right? A balloon, flexible, it'll just collapse on itself, so you can't reduce the pressure. So that's something you can't do. You can increase the temperature, as in a hot air balloon. It'll get less dense, the balloon will get bigger, or you can change the gas that occupies it by changing the gas content. You fill the balloon. We looked at the guys in San Francisco with the weather balloon, essentially. Fill it with helium. Helium's lighter, or hydrogen. Helium's better, as you know. And it will rise because it's a different density at the same pressure. So, again, the same idea. So you know that within this balloon, the pressure that's acting in all directions, you can't sustain a different pressure in the inside than the outside because it's not a rigid skin. This is a rigid skin. And so that might be a good thing to think about. Okay? All right, what else? I didn't really talk about what we would do today. We're going to talk about pressure on structures, blah, blah, blah. We talked about lots of disasters. We should be feeling happy that we're still alive today. We want to do three things. We want to know how the forces, how big they are. We've just done it for the cabin skin. How do we resolve them? Their vector sums. And most importantly, where they act. So you can imagine that if we're looking at a structure like this, we want to know how big is FH. We want to know where it acts compared with the other components here to resolve them. And the reason we want to know that is that we want to define a failure mode. So for instance, if we know, for example, that FH acts through this point here horizontally, and that W acts vertically by this amount, we could show that the resultant of those vectors goes beyond the toe, which means that this thing will roll over just like a domino falling over. If the resultant is inside the toe, it won't do that. It'll stand upright. And so those are the three things we want to do. We want to know how big, we want to know where it acts relative to the water pressure distribution, and then be able to resolve it. The short answer to this, in 2 seconds before we go through derivations, is that just by looking at this pressure distribution, you could divide it like this. You can see that this area here is exactly the mirror image of this. And so if you calculate the height of this centroid halfway down, which we'll call h sub c, then immediately you could calculate the value of the horizontal force as equal to the pressure times the unit weight. What's the pressure at this point? Pressure at this point is uniform all the way along here, so it's equal to hc gamma. Sorry, that's not right, is it? You should have told me that's not right. What should be there? Thank you. So that's where we're going to get to there. We perhaps go a different path, but that's the bottom line. This equation is always right. If you can define exactly the centroid of the plane that you're applying the force on, which would be the back of the dam. So this would be the back of the dam, this would be the angle of the dam. The centroid of that plane at the back of the dam is the balance point of this piece of paper. X, hold it here. And so this expression is always correct, and you'll see it 2 pages behind. Has it lost connection or something? Oh, the spinning rainbow of death. Oh yeah, perhaps I was doing something. So this expression here is always correct. We'll derive it. This expression just means that if there's a horizontal force and there's a vertical weight, the vector sum by Pythagoras is just this, the resultant. And we might need to know that. But we need to know also where it acts as well. Because it matters in this particular example whether it acts here or whether it acts, you could imagine that it might act at this point, right? That would be logical because that's the depth. It doesn't. It actually acts at, for this particular distribution, 2/3 of the total height of the water. Standard result. And the reason is, if you have a distribution of the pressure, if you wanted to calculate the centroid of that, you would bisect this angle. Must have had this in statics. You'd bisect this angle, and you'd bisect this angle, and the balance point would be here, and that is equal to 2/3, 1/3. And the physical idea is that, I don't know, sometimes I think this is more confusing than just going through the stuff, is if you imagine that you have a distribution of pressure, the origami king here, if you imagine having a distribution of pressure that looks like this, right? This is on the back of the dam. then this is the balance point. So this is the balance point here, if I could do that on my finger. This is the centroid of the pressure distribution, is where the center of pressure acts through that point. And it would act horizontally for a horizontal force, which we're acting here, and it just happens that the standard result for this particular distribution is that. So that's the punchline. If that makes you happy, but we'll go through a bit of derivation to be able to show exactly where that comes from. So, right? Questions? So you can get away with using. So I'm going to go through this in a bit more detail, but you essentially need to, from this week, use these standard results. The force acting is equal to depth of the centroid multiplied by unit weight and area, because this is the pressure that's acting, average pressure that's acting on the area here. You can resolve forces by using this, and you can always calculate where it acts by using these slightly complex formula, which we'll describe today and tomorrow where they come from. But you can use them as standard results. Okay. So what we're going to do, all right, let's do this. This is pressure. Don't know. Is my writing actually okay these days? Not too horrible? I don't look up for the answer, of course. Pressure distribution like this. We'll call this Y in this case. Remember we talked about Z upwards, but let's not use that today. And this is P is equal to gamma Y in this particular case, right? And so what we could do is we could take, I'm going to use, gamma times Y, is we could take this as being the upstream area, there, or the upstream face. Again, this is Y, this is H, this is W across the top, say, in the X direction. And what we can do is we can draw across here, and we can define a force that's acting, and that is that force is equal to pressure times area, which is equal to P times W times dy. This is dy. And so, let me get fancy with this. I love this one. And so we should be able to write an expression that force, this is d force, I guess, dF is equal to pressure times W times dy. Pressure is equal to unit weight of water times Y, which is equal to unit weight W Y dy. Zero to H. And if we do that integration, we just end up with F is equal to unit weight times W times a half Y squared. Should be right. And if we substitute for the limits between 0 and H, this is equal to unit weight W Y times a half Y. Oh, sorry, not Y. Have to substitute, right? H times a half H. And you've seen that already. This is the resultant. It's equal to unit weight times WH. This term here, not divided by, but this is the area, obviously. And this is H sub C, half the height. In other words, it's the height, so this is H. This is H sub C, which is half H. And we know exactly what that is because we can draw a line down here at that point. And if I'm going to use my nice colors again, we know that this volume, this area here, exactly substitutes this area here. So you can negative this one, minus VE, and add it here, positive, to get that. That's it. That's all it is. So that's where that comes from. And it's absolutely universal. You can use it. So if you imagine that you're below the surface and you have a plate that looks like this between, it happens to be, the pressure at this point is going to be H1. So this is equal to P, what's the pressure here? This is equal to unit weight H1. The unit weight, the pressure at the other end is going to be higher. It's going to be equal to H2. This is going to be unit weight H2. And just from looking at similar triangles, you can see that this geometry, if I do this, I didn't draw it very well. I'll draw it again. Should be up here, right? So this area here and this area here match. This is halfway along the system. Halfway along the system gives you this point here. And the depth of this point would be H1 plus H2 over 2, is that right? If you add them together and divide by 2. I think that's right. Anyway, this is HC. The depth of the middle, this is H sub C. Okay, that's it. Nothing more than that. Yeah.
Where did the 1/2 go in the...
This? The depth of the centroid is half H.
Yeah, but in the final...
In this one?
Yeah.
This is, well, if you add these together, this value is going to be this value here, right? I think. Or do you have to subtract them from each other? No, the average of these should be this point. Check it out. Put some numbers in it. Check it out. Okay? So, we know FR. Standard result, always true. You just need to be able to define the location of the centroid. Not divided through by A, but that value of the width times the height of the vertical structure in this case is equal to A. Obviously, A in this would not be the heights, it would be the perspective view. So in this particular case, if you wanted to calculate the pressure on this resultant pressure FR, it would be normal to the plate, and it would be equal to the unit weight of water, in this case, the area of the plate, which would be equal to W times L, in the plane of the plate, times H sub C. And so, in other words, we'd be calculating it here. And I've drawn it as if FR is acting at the middle of this plate. It's not, right? We know. It's always going to be actually below this centroid on the plate. Okay? So taking it nice and slow, bit by bit. Always works, always works. Area of the plate, in the plane of the plate, depth of the centroid in that plate, which is given by just the the crosshairs where that balance point is on this, and the unit weight of the fluid that's around it. We didn't worry about it in the plane, right? For two reasons. One, because it's horizontal, and so the centroid is going to be in the middle on the same plane, same horizontal plane, not the airplane. But also because it's a gas, right? Essentially, if we go up or down a little bit, the self-weight of the gas as you go from one to the other doesn't change very much because it's air. So it's inconsequential. Compared to 100 kilonewtons acting upwards and 20 kilonewtons acting downwards, the change in pressure with elevation over the height of a cabin, 5 meters, I guess, for this free body diagram, we don't care. It's trivial. We could include it, but you'd find out that it just dropped out. Okay? So ready to go on? So the next thing is where do they act? So that's a bit trickier. So, but still well within our capabilities, even on a Monday morning. So what we can do, I guess, is that we can look at this. I'm just going to draw. I could have copied the figure from above, I guess. No different. I could copy these things down and then race through it just by pointing at them, but that's not my style. And I think that's not always productive. P equals unit weight times y. This is the y direction. Same. Am I going to copy this? Yeah, I'm going to copy it. It's going to work. Oh! Yeah, okay. Now let me draw a separate diagram. So, what do I want to do? Yeah, fine. Let me draw it on here. So this is FR. So FR is the resultant force, and it's acting at the place where it acts, and it's a depth YR below the surface of the liquid. So if I do that here, what I can do is I can write FR YR. And what I'm going to do is I'm going to take moments around this. So to counter that moment, I have to apply the moment, which is MR. And in terms of moment equilibrium, clockwise and counterclockwise, this is equal to FR YR. That's just same as F equals, just the balance of the moments that are present. And so I'm going to do the same thing as before. I'm going to write the moment as equal to moment is going to be equal to dF times y equals the pressure times the area times y, which is equal to gamma y. Area is W dy. And the moment is y, and that is equal to the moment. So let's see if I can do this without screwing it up. Always a possibility. Love those integrals. So it will equal the moment is equal to the unit weight times W times y squared dy, which is equal to the unit weight times W times a third y cubed 0 to h. So the moment is equal to unit weight times the width. Let's take one of these out. So this is now not divided by, but this is the area, right, of the plate, times a third y squared. Hopefully that's right. And if we want to substitute, I guess we could substitute, which I didn't, but this would be equal to h, and this would be equal to h as well. I'm going to see if I can add something. Brilliant, fine. And so why we've put ourselves through this is that we want to be able to calculate what this moment is, and we know it as a function of this expression here. So if we know what FR is, we know what MR is, so we have a chance of being able to calculate this. So I'm not going to go off the page yet, so I can keep everything here. So we can rewrite this equation. We want to find out what this lever arm is. It's going to be equal to the moment divided by the force, the resultant. We know that the moment is given by this, which is unit weight times area times a third h squared divided by this unit weight area times a half h. Unit weight times area half h. And hopefully this is something we want. Get rid of this, get rid of this, and we end up with I actually did something right, and it's still not even 9 o'clock. We said this was right? This is the whole distribution thing. I'm not sure who did it. Where did I show it? I guess I showed it on the next slide, right? I made the point that it's 2/3 down, 2/3 from the top. And so the top, of course, is we're choosing this as our fulcrum for taking moments around this point here. And so when we come through with this, we end up with this. So, good. So a standard result for this particular distribution is that YR equals 2/3 H, specifically for this pressure distribution, which is triangular and goes through 0. Has to go through 0. So this is H. This is 2/3 H of the way down. And this is exactly where that force, that force is acting here. So this is the resultant. So, 10 minutes to go, but recap, make the mental note. You calculate the magnitude which is the resultant, which is equal to the unit weight times the area times the depth of the centroid of that area. But point of action is YR, which is equal to, in this case, 2 over 3H, specifically for this. But more generally, and you can see it's always below the height of the centroid, right? This is half height. This is where you calculate it. It's always below that. It can only ever be below it or equal to it. If the plane was horizontal, it would act directly in the middle of it, so it would act exactly at the centroid, but it can never act above this point H sub c. And I won't bore you with the derivation, but the generalized form of this expression is this. Don't know if we'll have time to do it. So the general expression is this. And these things, let's do it for this. So in this particular case, you've had in your statics, IXC is the second moment of area about X, which is equal to, if we have a plate, so our plate is this. This is W, this is H. We said that the centroid of this plate for a vertical plate is through here. So this is H sub C. This is Y acting downwards, hence the term YR. X sub C is the second moment of inertia, which is a 12th W H cubed or squared? Cubed. Standard result. Y sub C equals the location of the centroid, which is equal to HC, which is equal to H over 2. And area is equal to YCA, which is YC multiplied by the area, which is WH. And so this term you can think of that the point of action of the resultant, which I'll show in green, this resultant acts at this point here, which is YR down, and it's equal to the height of the centroid plus some small amount, right? This would be YC. HC is YC in this. The reason for making the distinction is this plate is vertical, but it could be inclined, in which case the y-axis is inclined along the length of it. We'll talk a lot about it next time. All I want to show today is that this result gives us also the same result we had before. So what have you got? YR is equal to 1 over 12 width times height cubed. Didn't want to do that. This is cubed. This term here. Divided by YC is HC, which is a half H, right? Area is height times width plus YC is equal to half H. See if your math is good this morning. So what's this? This is 2 over 12, W's cancel, times H, plus a half h, which is equal to 2 over 12 plus 6 over 12 times h. The boy's a genius. Okay. Standard result. And so it allows, so again, make the point. We can calculate the magnitude of the resultant. The resultant is always this equation. The resultant always acts normal to the surface of the plate. Plate can be vertical, as in the back of the dam, or it can be inclined. If it's inclined, the resultant acts normal to that plate. The location where it acts is always given by YR. A special result for this case where the water is here and we have a triangle distribution, it's always 2/3 down the height of this distribution. Not true if it's inclined. Did I draw it somewhere else? I did draw, yeah, I drew it somewhere else, right? Where did I draw it? Not true if it's inclined, can't find it. And the universal result for the depth of action of the resultant, the point where it acts through, normal to the plate, for a planar plate, is given by this equation here. And you can think of this as being equal to YR equals delta Y plus YC. This is the location of the centroid, which is this point here. It's given the term Y because the plate could be inclined, in which case the Y-axis is in the plane of the plate. And this delta magnitude is the distance below this. I guess it would be this amount here. This would be delta Y, not AY, delta Y, below it as is. Because this is always a positive number, the point of action always has to be below or equal to it. It could be 0, but it has to be always positive in terms of the parameters in there. And we'll use that next time, I think, to do some examples to figure out. So you've avoided, yeah, so we'll talk next time about that. All right. Off to a good start. Thanks for your questions. I know it's a lot of math. I mean, you just need to use these results. You never need to derive them, but it's useful to understand where they come from. So we'll talk about using some on some examples next time.